Morning, everybody. Today is Thursday, June 15th, 2023. This is the Podman Community Cabal meeting. We'll be talking today about additional layer storage. And we have Jerry. I'm going to mess up your name, Jerry. Is it Seidman? Seidman. And then okay. And then after that, we've got a talk that's kind of a generic talk for IPFS integration into Podman. Anders was going to at least kick that off. I don't see Anders yet. So we'll see, and I know Dan had wanted to talk about that as well. And so, I have HackMD set up where I'll be taking the notes today. If you have links or anything that you want to add to it, or if you find that I've misdescribed something in the notes, feel free to go ahead and change those as you see fit. And with all that, I'm going to hand it over to Jerry. Thanks for coming today, Jerry. And I'll stop sharing.
First of all, if somebody could just check that works. That should be the my presentation slides. If not, let me know, because some people like to follow along as PDF. Oh, I could have put them there. That's a good point. All right. Nobody's going to confirm or deny?
Well, I was while I was muted, which was very helpful.
Oh, did you get it?
No, I cannot. It says I need access.
All right, hold on. Anyone with the link? Not. Let me do it again. And
now we see it.
You got it?
Yep.
Excellent. Because it'll make it easier for everybody. Because I'm going to talk fast. I'm from New York, and I have too many slides. Hi, I'm Jerry Seidman. I'm president at Orastore, which is a company that has a secure distributed file system. I'm going to talk about our core product. I'm also going to talk about what we're doing in the container space, or what we're doing for accelerating start times for containers. I'll just get started because I have a lot.
Did we lose Jerry?
Jerry, you're muted. Jerry, you're muted. I see infinity.
All right. Can somebody now say, yes, Jerry, I see your slides and I hear you?
Yes, Jerry, I see your slides and I hear you.
Yes.
Nobody?
Oh,
yes.
We can hear you.
Wave if you can hear me. Christopher, can you hear me? Okay, so I can't hear you for some reasons, but that's okay. If you have any questions, I'll jump out. Got it. Okay, cool. All right, so I'm going to go very, very quickly through a lot of topics. One, I'm going to talk about what is Orastore FS. I'm going to frame the problem that the Orastore Container Accelerator solves. I'm going to very, very quickly talk about container storage internals, which most of you should know better than me. I'm going to talk about additional image store, which Dan certainly knows better than me. Then I'm going to talk about additional layer stores. That's a typo. It should be additional layer stores storage. And then finally, I'm going to talk about the Orastore Accelerator. Actually, I'm going to be talking about that interspersed with a bunch of other stuff, and then just a few slides specific to it. So Orastore FS. It's the cloud file system for the 21st century. That's actually a joke because the Orastore file system has its roots in the Andrew file system, which predates NFS. It was designed very presciently. But the reason, Orastore's initial funding came from the Department of Energy, and we got an SDIR to create a 21st century cloud file system that extends upon the AFS vision. So that's the joke in that. But it was designed to do a lot of things, and Orastore extends very much beyond what the open source AFS does, and certainly what anybody who used AFS a long time ago might remember. But here's the kind of the high level points, and I'm going to drill into some of them. A global namespace, a true global namespace that actually can span organizations, not just clouds. Access transparent, it's just a file system. Files are files are files. Again, for definition, in this case, I'm talking about the file part of a file system, not block storage. It's highly secure. I'm not going to go into the security model at all. It has a cache consistency model. What that means is that there is a local cache on the machine on each client, and if something changes on the server, it's the server's responsibility to inform the client. Which means you don't have to do polling, and because it's done properly over version, kinds of things like that, the cache actually survives a reboot. It's platform independent. The clients run on pretty much everything. I'm going to talk more about that. An AFS is I'm going to talk about AFS volume separately. High availability, works well over the WAN as well as the LAN, boundless scalability, and like I said, hybrid multi-cloud by default. I'm going to just focus for a minute on these because they're just cool. What I mean by a global namespace is if you just take a fresh install of Fedora and anything over 431, there's a bug in 38, but you just, if you do a fresh install, you ls/AFS, there's nothing there. You install the CAPS client, there's an upstream Linux client that's in the Linux mainline as well as in many distributions like Ubuntu. Not yet in RHEL, but we have a signed version if you're running RHEL 9.2. Reach out to me and I can give you this client. You just start the AFS .mount service, and then if you're running, there's a bug in Fedora 38 where you have to set enforce permissive. You don't in Fedora 37, and you won't in Fedora 39, and hopefully not much longer in Fedora 38. And then just say, make believe you're an astrophysicist or a high energy physicist, and just look at files at CERN. ls/AFS/cern.ch, and lo and behold, it works. Zero client configuration, global namespace. Access transparent. It just looks like a file. So I'm going to just add a file from CERN's Atlas project, a script from their Atlas project, and it just works. And as I said, it's platform independent. On the one side I have Windows, and the other side I have Linux. Now I'm going to focus on the parts that are salient for ALS. The cache consistency model and the AFS volumes with policy containers, really more about the AFS volumes. In AFS, again, volume is a highly overloaded term. In AFS, a volume is just a rooted directory of files, and it can have files and symlinks and directories, etc. An example of a volume, read-write volumes would be, for example, training data, machine learning training data, models, data sets, application binaries, configuration files, static web content. For read-write, your home directory, scratch space, log, some specific project, etc. Volumes are the unit of management in AFS. It's the thing you put policy upon, things like quota, replicas. So for example, if that's something that I want high availability, I might serve it up on 3 file servers in New York, 2 in Shanghai, 1 in London. It's still globally accessible, but your client will find the network closest one to get you the best performance. Maximal access control is a security thing. Things that you could do, things like this data can't leave the US. It's got a lot of cool stuff. But an AFS volume, the AFS unit of management is called a cell, and cells have volumes in them, and volumes have human readable names. So for example, I could have a volume called language-model .training-data. So that would be where I would put it. I didn't say how to access it yet, but and there's also a special volume with the name root.cell. again, there's volumes. I don't know why I have a separate. Oh, in this, what I'm showing is that within an AFS volume, you can link to another AFS volume. That's what these triangles are for. Yeah, the triangles are showing. You can actually have hard links. You can actually have hard links as well as sim links within a volume. You can't do cross volume hard links, but you can do mount points at the volumes. So how you access it in well, actually I gave you this is the syntax not for CAPS but for our proprietary client. But anybody can reach out to me. I'll tell you how to do it or look up online. /AFS/dot mount /cell name /volume name gets you to a volume. You know, that just works. There's also a dynamic route called /AFS by default. It could be anything else in your system. It doesn't have to be global. A lot of our banking customers, of course, have it only locally accessible. And that's how the global namespace works. So I'll get back to that with an example. But you know, here, for example, somewhere on my file system, I might want to have my chat ABC language training data. I want to mount it there, so I just say dot at. I could do ln-l /dot at mount /blah blah 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 blah, because /AFS/dot at mount /myorg.com /language training directly gets me to the root of that volume. So if I link it symbolically there, I now have it anywhere in my file system. Again, that's the syntax up here. But the cool thing, one of the cool things is dynamic zero configuration global namespace. So there is that I mentioned in passing a /AFS directly off of the root. That's now actually a reserved name. You can't. It's a Linux official thing. /AFS. You can't have /AFS be anything but this. And the way it works, if I go /AFS/umichigan.edu or cern.edu, there are DNS service records that say where the metadata servers are for University of Michigan or CERN, etc. And what happens is the client, when you say /AFS/cern.com, it goes to DNS and it finds the IP address of the metadata server, and then it dynamically mounts the root.cell, that special root.cell, at /AFS/shellname. Last thing I want to say, the penultimate thing I want to say is AFS, every AFS volume is really an object store. It's not really a file server, it's an object server where each volume is an object store and each entity in it, files, paths, files, links, directories, etc., are objects with their unique object IDs. And actually the server doesn't know anything about paths, unlike NFS. The path is all the path work interpretation, path to object ID interpretation is done completely on the client. As I said, also said there's a cache consistency model that survives reboots. So when you read from the file server a fraction of a file, not the whole file, it's not a copy and sync file system, it just grabs the blocks that you read, it stores it in the cache with the least recently used caching, and the cache can be very, very large. It can be a couple of gigabytes, it can be a couple of terabytes. So for example, if you're doing like some machine learning stuff, you might want to have a very large cache. So you're not pulling things off the network so well. All right, that's all. We now are all experts in Forester.
Jerry,
now I want to talk a little bit about containers as software deployment.
Jerry,
inheriting all the classic problems of software delivery. So very quick slide, just we all know this, that at runtime, you're using you've got an overlay file system with the presented to the container at runtime, where the root is the read-write layer, and then there's a list of read-only diff layers. On the local machine, if you built a container with a bunch of layers, you have all the files locally. In particular, you also have a manifest and a config file, whatever those are. It's a well-defined manifest. It just tells me about the container image. But when you say .podman push, it takes those files on the layers and creates a tar.gz compressed version, and that's what goes up to the container registry. And the container registry stores them. And in fact, the container registry is basically an object store where the manifest, given a docker.io / library / Alpine, you go to the registry and say, hey, what's its unique ID? What's the ID of its manifest? That's the only time you use. It's not object-like. Anyway, and then from there on, you just bootstrap and say, give me this object ID, which gets the manifest, and then give me this object ID with coming out of the manifest of the layer ID to grab the layers. And when you say pull, you do the opposite. You pull the layers and you untar them locally onto your local disk. So what are the associated costs with pulling a container image? There's the clock time spent downloading the entire tar.gz file, which for large files can be not insignificant. And the cost of the network bandwidth, any CPU and I/O spent expanding that tar.gz onto local disk directories, and the disk space required to store them and expand them. So you're effectively, your container start time is the download time plus the expansion time. And again, these costs are only incurred the first time the layer is pulled. I say container image, but it's per layer. So large container images are not uncommon. Python is 1.1 gigabyte before you do anything. We have I know of customers that have just taken legacy systems and made them into one giant 40 gigabyte container. And then an example of that would be SAS, if you remember the old statistics programs, SAS. That's what they did. They're not a customer of ours, but they have one. I think theirs is like 50 or 60 gigabytes. They just made one giant container image. Big deal. I'm only downloading it once, no problem. So if I got a 1 gigabyte app, I download it to my machine or my server, I got it. The problem is, as it scale, this adds up. So if I'm deploying 1,000 1 gigabyte images to 1,000 machines, if I am delivering a single gigabyte image to 1,000 machines, that means I've got to move a terabyte over my network, which is, you don't ever want to start a sentence, move a terabyte over your network. And certainly if you're in any industry where the network has to be really smooth, like a bank or anything that's doing experimentation on it, you don't want that choppiness of the network caused by a lot of pulling of images. And again, running 1,000 machines isn't uncommon. I mean, we have enterprise customers that are running, they're actually running applications on almost 200,000 machines, tens of thousands of applications. Not uncommon for a single application to go to 1,000 machines, and then be distributed across the enterprise, both locally and globally and cross-cloud. So that's not uncommon. And we also have customers that have compute clusters, HPC compute clusters where they got 1,000 nodes, and they'll just, blow out the container image to the nodes in the cluster. So that's not that 1,000 is not unrealistic. The other thing is that if you're running lots of containers on a single machine, either individually with Podman or orchestrated by Kubernetes, you can have a lot of containers on a machine, and that actually causes bloat in the disk. Just by the way, well, this is the Podman group. An OpenShift node, if you've configured it with a bunch of stuff turned on, can be up to 100 gigabytes of operator images. So you're actually, when you're creating a new OpenShift node, you could be pulling as much as 100 gigabytes of container images. And there are many factors in the time, but it takes about 45 minutes to set up an OpenShift node. Okay, so now we know, big is bad. They're expensive. So an important observation, and this actually goes back, this is a software delivery problem, software deployment problem, goes back to cards and tapes and disks and CDs and RPM files and containers, that many of the files in the software deployment and the container image are just not used at runtime. They're just not used. unless somebody put a lot of work into culling their deployment, pretty bloated. In fact, going back to a paper back in 2016, there's a link by Harder. Pulling packages accounts for 76% of container start time, but only 6.4% of that data is read. That was the result of their studies, their analysis. It was a few years ago, but I suspect it's worse, not better. But there you go. So in that prior example, if I'm downloading if I'm pushing 1,000 copies of a container to a 1 gigabyte container to 1,000 machines, that 1 terabyte would go down to 6.4 gigabytes, right? And there's an opportunity for local reduction of storage, actually for more than because the tar files expand. Again, for a single image, it's not important, but if I've got a machine with many images, I could have hundreds. I may have hundreds of gigabytes of actively used container images on a server or a Kubernetes node. I'm not going to dwell on this. This is from that 2006 paper about some example slides. I go back. I'm sorry. Let me go back. What was their research? It was fast distribution of lazy Docker containers, and they had this idea that if you could create an index into the tar.gz file, you could just cherry pick the blocks of the blob using HTTP get range instead of just HTTP get all from the container registry. And so their whole paper is about creating indices and creating these non-standard container images. So this is from their non-standard implementation, but still they're getting pretty impressive compressions and pretty significant start time improvement. Okay, again, because it's only pulling down the files that are actually used as runtime. So let's now take another digression on container storage, because then this will all come together. Because my feeling is, never use a technology you don't know how to write. So I'm basically going into the internals of how this all works, so you understand how it works, and that way, hopefully everything is clearer. Container storage. Again, this is talking to the choir, teaching the choir, or not even preaching. That you've got the storage.configuration file, storage.conf file, and then you have a local working directory where the container layers and images, information are stored, and at those respective paths. This is all implemented in the container/storage and container/image subsystems of Podman. So I'm just for laughs, I'm just starting with a fresh system, I say Podman images, and what that does is that actually populates the empty graph of the structure. I'm not going to drill into everything, but that's kind of the structure of storage at runtime with Podman. And if I look at it when I just created empty, it's about 32K. All right. We're only going to focus on again, in these slides, the things in green are the things I'm for me to remind myself to talk about. There's the overlay storage, and that's actually, the storage/overlay. That's where the actual files are stored for the layers. And overlay/images, it's where information about the images is stored. Because again, a layer may be used by multiple images. All right. So again, doing something simple like a .podman pull. It gives us it throws out this number, which is the layer ID, the layer digest of a layer, outlines a single layer container. Everything I'm saying works on multi-layer containers. It pulls down the manifest file, and then it copies the signature, and then it echoes back the ID of the registry, the ID of the container, the image. That's the ID. That's the digest of the container image. And so we'll see these numbers again. Is 31E blah 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 is the layer. C1AABB is the image. So looking inside the overlay images file, we see there again corresponding to the image ID of C1AAA. There's a subdirectory C1AAA with junk under it, but it does include the manifest file. And the way to find the C31E35 is not that's the actually manifest ID, the digest of the compressed image, not the uncompressed image, which is what actually which is actually what's used in the manifest file. So the way to find the actual digest of that layer is doing stuff. Extracting stuff out of the JSON file, out of these JSON files. Again, I'm not going to talk it through, but the point I'm making is that you can now forget about the 31E blah 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 because it maps to one to one to the 7A 78A blah blah blah. Is what we're going to watch. So again, now let's look at the overlay folder. We see that there, lo and behold, is a directory corresponding to that layer with some files, the salient file being the diff file, which contains the diff files from that layer, and I can go directly in and see those files. All right, so we're now, and then at runtime, at runtime, you need, what will happen is we'll see a second container layer is created. That's the read-write layer. That's the transient read-write layer of this container. When the container ends and you remove, Podman RM, that layer will go away. But I just want to, be clear that if I can, if I run the container and create some content in it, I can see it actually under overlay. All right. So now we're all experts. We all probably were experts on this before I started talking, but now we're reminded experts. So now we're talking about additional image store, not an additional layer store, additional image store. Briefly, additional image store allows you to have multiple instances of that structure that I just talked about, and you specify. And you have one or more of those, and those are configured in the storage.conf file under additional image stores. And what it works exactly like when you do a pull, it looks like any pull, but you pull into a specified copy. So you have actually that directory structure multiple times in multiple places. All right, depending on how many you have. And so if I pull BusyBox into that, and then I go into that directory, the temp/AIS, you'll see, lo and behold, I get exactly what I saw before. But the AIS will only be read-only. You will never, ever it's only for the images, the layers from downloaded images, the read-write layers. At runtime, it will always put the read-write layer in your primary root. But notice I left something out. I just want to be very clear when well, there you go. When I ran Alpine, 7.5 megabytes. Okay, just remember that number. 7.5 megabytes is the size of Alpine. BusyBox is smaller, 4.8 megabytes. And when you do a Podman images, now you have an extra column with an additional image store, which will tell you whether it's your read-write layer store or it's coming from one of your read-only layer stores. Okay. So what's the value proposition of this? You get to share read-only layers across multiple users. Now, for example, if these are the alternate image stores is on a single box, as you know that in Podman, rootless Podman, every user has their own directory structure corresponding to storage. This would allow you to have a single place rather than having every user on a machine downloading the image. They can get it from a shared place. Another use case is you download it into an NSF share, and now you have files that are being pulled on your local machine from an NFS share. And so you can have, instead of having copies on every machine, you can have copies just in the NFS share. All of this because of the pull into the alternate layer image store. It has to be administratively managed. Somebody's got to do something to do that, whether to do the pull into locally or the pull into the NFS share. If you haven't read it, there's Dan Walsh's article on exploring additional image stores in Podman. So the bottom line is Podman works pretty much, additional image stores is pretty much standard. It just allows you to have more than one. It allows you to have extra read-only. Now, to be contrasted with additional layer storage, ALS, which the history of ALS is goes back to that Carter paper where they tried to create a again, as I said, a way to lazy load containers by having an index into the tar.gz file that was seekable. That's what the essence seekable tar gz is what that stands for. That's what they did. I'm not going to dwell on it, but the original proof of concept for ALS was done by a group of NTT engineers who did the heavy lifting of implementing what the harder group did, but in actually container/storage, container/images. No, actually, it's just in container/storage, as well as in containerd. And it is now shipped. It is in Podman today. So ALS provides additional sources of layer content. Not about the whole structure of the storage. It's just the layer content. There are actually three examples of uses of ALS: the StarGZ, the NTT one. CERN, I think, has one, but I think they may have walked away from it. There's an IPFS implementation, and of course, there's ORIS. So the way you implement ALS is with a fuse driver, because you need some sort of RPC from the container runtime to say, hey, I've got a layer. I need the concept of a layer. Can you provide it? That's really what happens at runtime. But before it downloads, it says, do I have the files locally? If not, it says, hey, you fuse file system, can you provide it? And you specify the root of your ALS fuse file system under additional layer stores in the configuration file. And so what happens is at runtime, there's an intercept. If it doesn't already have the files, it asks you, can you do it? And if you say yes, if your ALS says yes, it basically says, okay, great, give me your root, and I'll get the files from you. We'll see a little bit more detail. So here, so in this example, I have my ALS, my ORIS store alternate layer storage root at jerry/home/ACA/store. By putting that in your config file, it's telling the container runtime to look when it wants to query you. It uses the fuse as a query language. It's kind of an RPC. Your fuse root / your ALS root / the basic D4 of the image reference / layer digest. And that's where it's expecting you to provide the diff directory, as well as an info file and the raw blob, if it asks you for it. It never does, but all right. So again, you have to satisfy the ALS RPC by being able to service these paths these paths by your driver. So now let's look again. So here's the same thing I did. I have a blank, fresh container storage, the 32K. I do with my ALS driver running. I do a Podman pull. Everything's the same. And now I look and do a disk usage on it. And instead of being 7.5 megabytes, it's 1.4 kilobytes. 104 kilobytes. And that's not going to change. That the caching is done on AFS. That's a different, that cache is in a different place. So in this case, we've reduced the container storage size by quite a lot. And the interesting thing is, when I did this Dr. Pull, nothing came over the network. Nothing came over the network. All that happened was the ALS driver said, I can provide the services, I can provide the files. You didn't ask for any files, so I'm not doing anything yet, but I'm saying I can give you files at those directories. So now let's look in the store, or that's actually overlay. No, under store, actually this is the ALS route, what my fuse file system is providing. And it's under my fuse, there's a route with the base 64 encoding of, I guess that's docker.io/alpine or something like that, the digest of the layer, and I have to provide basic people of the reference /layer digest /bob/diff/info, and doing a little forward thing. Notice that what am I doing in my Aura Store ALS implementation? I am just doing a link to volumes. I'm just doing a link to a volume on the cell dbb.imx.com with the name J1 blah 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 blah. Coincidentally, with a name very similar. I'm truncating the names just for ease of use. And again, just to prove it, I did an echo of that Z blah 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 through base 64 decode, and yes, in fact, it is docker.io/library. Now going back to container storage, what I'm seeing is under that directory, under that the map digest ID, I see under the diff, rather than the files, which I saw before, I just see a symbolic link. Again, that's what it really is, but below I kind of abbreviated. So the layer under storage /overlay/layer digest /diff is really a symbolic link into that AFS, into that path, that ALS path, which in fact is going to give you the contents of the Aura Store volume. There I'm just kind of showing you that it really works. The /info just gives you the standard information, standard interpretation of the information of that layer. That's a container image standard. And if I do a stat-l of the blob file, it says that in fact, if asked, the Aura Store LAS driver can give you the tar.dg file of that layer, and it's going to be 3.4, 3.4 megabytes. And of course, if I run the and if I just run it, everything runs as normal. So again, the only I ran this, and the storage size went from 7.5 megabytes to 104 kilobytes. So that's the trick behind ALS. There'd be many. You can put NFS behind ALS, but the fundamental difference between ALS and AIS is that AIS has a complete replication of that sort of complicated structure, which allows it to reuse a lot of code. It's using the same code as container storage, but with ALS, you're just grabbing the layers direct. All right. So this is currently deployed in Podman. You can run it today in Podman. But if you look in the source code, it says experimental. And if you look at the man page for storage.conf, there's no reference to it. So one of my missions is to get it promoted. Dan suggested the following route: give a presentation to the Podman Cabal. Write a blog article about it. Update the man pages so storage.conf describes additional layer store, and create some ASA tests that can be run in the continuous integration testing for the storage library. So finally, the Orster Container Accelerator. Again, I really gone through it already. All it is a fuse driver. At runtime, it's a fuse driver that maps those munged names of container image references / layers to AFS volume names in a well-defined manner. So how is it configured? Actually, look at this. I actually have in a cell, I have this layer volume set file. So actually, that path is the same path that I put in my ALS. In the configuration of, not configuration of storage.conf, in the ALS client configuration. I give it a path to say, bootstrap. I don't want to put information on. I'm a distributed file system. I might as well have the configuration where it should be. And what that's saying is that the cell name adc.xyz.com will service layers from these repos, and these are prefixes, from these repos, and you will find it in that cell under the layer name J1 underscore blah, where the blah and I strip out this SHA-256. That's the same. So that's the mapping to find the Orster volume from the layer, from the image and layer. Why does it work? Where are these layers coming from? There's a service called the Orster Layer Volume Generation Service that either can be hooked via webhooks to your container registry, or through a command line tool where you say lvcuddle ingest docker.io/alpine, and all it does is it goes to the container registry, it grabs the manifest, and then for each of the diff layers, it says if I haven't already created an AFS volume corresponding to that in the appropriate cell, I download it and I untar it, and then I create an AFS volume with that. And so that's what the layer generation service does. That's it. So now I'm gonna stop sharing, and I think I was not too over, and I haven't heard anything. So hopefully,
Can you hear us now?
Did people hear it? My presentation?
Yes.
Good. I can't hear you. Could somebody say something?
Yeah, we're trying to talk.
Are
You
your
can't hear us.
speakers muted? No, they're not. Okay, so people are speaking. I'm going to just.
Can you hear us now?
Okay, Tom, you raised his hands. Are you speaking?
Can you hear anything at all, Jerry?
Hold on a second. I'm sorry.
I was hoping you could check chat.
My
Can you hear us
Bluetooth.
now?
I'm having technology problems. I apologize.
Test, 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 test.
I don't think he's on board yet.
I can hear you.
Oh, you can hear us?
I can hear you now. Yeah, my Bluetooth
Okay.
picked out, I guess. who knows? All these screen sharing things do weird things to Bluetooth, and it turns out the speakers on my laptop don't work, so I had to put an external speaker in.
Okay,
That's
so
where I ran out. I
we
apologize.
have a couple of questions that were queued up while you were talking and we couldn't get your attention. So
Absolutely.
Chris had one that was, can AFS volume store extended attributes, i.e. SE Linux labels?
Extended attributes are currently not. Okay, they're currently not supported. They will be supported in the next release of Aurastore. And I'm guessing you asked that because the overlay file system wants the extended attributes. Well, it turns out Podman is good. Kubernetes OpenShift is bad because Podman defaults to Fuse overlay FS. And with Fuse overlay FS, I can provide them just the .wh files, the whiteout files. But in the next version of Aurastore, we'll be able to do that. We're actually doing some other stuff. We're also doing FS Verity checking and things like that, which will make us the only distributed file system that can do FS Verity if and when you care, etc.
Okay, Jerry, I asked access control. Is that done on the server side or the client side?
Yes. There's a problem. Access control is an interesting thing because there's actually 3 different places where you have access control. You have the Unix bits that are in the container images. Those are preserved by container, the standard pipeline. There's the permission to download the layers on the container registry. And then there's the permission to access the AFS volume. All right, 3 different places. We can restrict a runtime application to access the files in an AFS volume. We can do that. We can put access control on the volume. We can't do it on the per file because that can't be represented. We actually can, but it makes no sense in the whole container model. But you would want it, if you really wanted to do that, you would want to have a container registry that would never serve the tar.gz files.
Yeah, because what we've seen in the past with, if I put stores on a network file store, for instance, NFS, it doesn't understand the user namespace. So if I'm in the user namespace and I tried to chown a file, the server says no because it doesn't want UID Walsh to chown to UID 100,000.
Got it. Yeah.
Yeah.
I don't think. Yeah.
Right. Would AFS work the same way?
Mm-hmm. AFS would work. No, AFS would work. I don't know why. It's out of my pay grade, but
so you think AFS would allow that?
I believe so. I could run a quick check, but I believe it does.
Okay.
But take that as a qualified yes.
All right. So yeah, when you were showing the additional layer store,
hopefully I didn't misrepresent additional image store.
No. Additional. Actually, I liked a lot of your slides, and it'd probably be helpful if we got some of those slides up to basically describe how this stuff all works. The ALS, though, you say there's a Fuse file system that's required. Is that Fuse file system open source at this point?
It's an implementation specific thing. The NTT one, the Start GZ one is. The Aurastore one is not.
Okay.
But it's a choice. It's a long story as to why Aurastore is not open source.
Right.
We'd love to be, we just can't eat and be open source.
That's fine. So you have a tool that is creating these additional layer stores.
Yep.
So you're populating that in a format that we can consume, that Podman can consume.
Yeah. I think it's this the layer volume, the image layer digest to layer the Aurastore layer volume configuration is shared by the server and the server that the service that creates them as well as the client. Yeah.
And lastly, there's
a little thing I want to also mention. Big organizations that have a lot of apps over a lot of time have a lot of problems with culling. When do you call something? And our customers are always asking, what can we do to help? And there's not a lot we can do to help because you can only at best infer certain things. But I actually and with container images, you have an even worse problem because you are you can be cached far away, and have it for a long time. And so we posited that we could get some usage metrics from our ALS from our fuse driver of whether layers are being used. Which will help
so if you had a layer that hasn't been used in 3 years, then you can get rid of it.
Right, exactly.
Okay. Anybody other questions? Anybody? So why would you prefer to use ALS rather than just doing AIS?
One is the dynamic nature of it, that there's no pull. The other with AIS is I would have to figure out how to do it because I'm mapping. I'd have to do something in image store to do the mapping from the appropriate path where ALS jumps off to where AIS or with storage. There's no AIS. It's just the standard storage, overlay / blah, blah, blah. I don't know how I would even hook into that without doing some plumbing in storage.
I guess lastly, the reason people have said they won't use AIS in the past has been latency. So that you're running a container, it's running fine for a long period of time, and then all of a sudden it decides to access some piece of data that isn't in cache, and it goes into a pause.
Yeah, I mean, yes. The answer is yes. One of the advantages of ALS over AIS in that regard is the cache. If you hit something that you haven't hit in a long time, it may still be in the cache. But with NFS, you're always doing it, whether you've loaded it recently or not, because the caching is much not as good. And one of the things they did in the Star GZ project, which we have talked about doing as well, to address that problem, is to create a manifest of files to pre-pull, to pre-populate, to seed the cache. When I was at Red Hat Summit, I spoke extensively with somebody who works as a cruise line, and a ship is one giant OpenShift cluster, and they have a lot of pain bouncing that off of a satellite network that's expensive and slow and lost and unreliable. So to meet their needs, we talked about adding functionality of, like I said, a seed set of these are files you should preload, and those can be obtained by observing prior runs of the application. That's already implemented in again in Star GZ. If you look at it, there's a way to somehow, I forget how, but somehow specify how to pre-pull. By the way, Star GZ is kind of funny because it solves the fast start, but by default it then lazy loads the whole image anyway. So you get a fast start, but eventually you have all the files.
Okay, I'm going to have to hold questions here because we are way over time.
So sorry.
Yeah, no problem. But thank you, Jerry. It was very interesting. And
okay. Did I post the link? I posted the link. You guys have it. Yeah.
Yeah, we have the link.
Hopefully that wasn't too fast.
Yep. No, it's fine. And so we were supposed to talk about IPFS, but Anders isn't here today, and I know he wanted to be part of that talk, so I'm going to push that out to the next meeting. Matt, it looks like you slid in a Podman 4.6 release schedule update. Did you want to talk about that briefly?
Well, let's delay until Monday. 4 minutes is a little late to talk about this, and I don't want to push us over.
Okay.
Or we'll delay this until next time we can talk.
Okay. Yeah, it's going to be a couple weeks out. Yeah.
Yeah, just for those, I guess we're not going to start for another week for 4.6 is what bottom line, right?
Yeah, at this point, we're basically, I would like to get things rolling, but well, we can probably get the ball rolling during the planning on Tuesday and then see things roll from there. I would hope to have an RC out in 2 weeks maximum.
Yeah.
Okay.
And our end goal for 4.6 is to have something out by mid to late August.
No, that's 4.7. And goal for 4.6 is to have something out very early July, hopefully.
Okay, but much more expedient than I had thought. Right. Given that, I think I'm going to wrap up this meeting and just, I do.
One quick question, if I may. It's
Sure.
really focused at Dan. When we met you, we talked about there should be a man page. Other than storage.conf, where would man information go? I can't think of any place because there's no
Just to go into storage.com.
just storage.com. Good.
Yeah.
Okay. I just wanted to confirm that. Thank you.
Okay. So our next Cabal meeting will be on July 20th, same time, 11 o'clock in the morning Eastern time. And then our next community meeting will be happening on Tuesday, August 1st. I'd like to thank Jerry very much for coming here and presenting today. It was great information and for everybody participating. And with that, I'm going to turn off the recording.